So identities are statements that are true for any values that we plug into them. We've already talked about some identities. One was the reciprocal identities, right? We learned these a long time ago. We know that cosecant theta is equal to 1 over sine theta, and sine theta is 1 over cosecant theta. Okay, secant theta is 1 over cosine theta, and cosine theta is 1 over secant theta. Cotangent and tangent, they're reciprocals of each other. So cotangent is 1 over tangent theta, and tangent is 1 over cotangent theta. Well, we learned these a long time ago, and I hope we are glad that we did. Okay, so that's one set of identities. What we're going to be working on is starting with the statement and rewriting that statement in a simpler form, and other things. So we'll start here. Okay, other identities that we might know. Skip those. Those are examples. Quotient identities. We've talked about these. We know that tangent theta is equal to sine theta over cosine theta. And cotangent theta is equal to cosine theta over sine theta. All right. And then there's the Pythagorean identities. Okay. We're already familiar with the Pythagorean identity. Normally we say a squared plus b squared equals c squared. Or in terms of x, y, and the radius, we can say x squared plus y squared equals r squared. Okay, that kind of describes a circle when we write it that way. Okay, and so what we want to be able to do is to state this in terms of sine, cosine, cosecant, secant, tangent, cotangent. And so let's start by looking at any angle, right? When we find an angle on the unit circle, first of all, we know that the length of the radius is 1, and we can have coordinates x and y that describe how we get to that point on the circle, right? We can go x units, left or right, y units, up or down. That gets us to the point. Okay, but we also learned that when we're on the unit circle, we can think of the coordinates of the point as what? Very good. Cosine theta, sine theta. So we got cosine theta, sine theta. All right, and so when I said previously, x squared plus y squared equals r squared, now I can write that as cosine squared theta plus sine squared theta equals 1. Okay? And that's the first of our Pythagorean identities. Okay? So cosine squared theta plus sine squared theta equals 1. In the middle of the night. That's one that I remember. Okay, there are two others, and we're going to look at them. Yes, Grace.
So I was just going to, so this is one of the here.
Yes. Mm-hmm. So I'm going to go back to that page. All right, so we got cosine squared theta plus sine squared theta equals 1. And, you know, I don't memorize a whole bunch of things. So once I do that, I can derive the other two. Okay? That is, use manipulations and legal mathematical moves to figure out what the other two are. Okay? And so the way that I'm going to do that is to divide through by cosine squared. Okay? In one of these equations that I set up here. So if I divide through by cosine squared, then this statement becomes what? What's cosine squared theta over cosine squared theta? 1. And sine over cosine is tangent, so it's 1 plus tangent squared theta equals 1 over cosine is what? Secant. Yes.
Why is tangent squared? Doesn't the squared cancel out?
Not if they're different. Okay. All right, so 1 plus tangent squared theta equals secant squared theta. Okay, so that's my second identity, Pythagorean identity. All right, so I can also divide through by sine. Squared theta. And if I do that, then we get what? Okay. Cotangent squared theta plus 1 equals, very good. Excellent. So those are our 3 Pythagorean identities. Okay, everybody okay? All right, now these are really useful. We'll come back to them several times today, okay? So when we start manipulating and trying to simplify, if I have one of my trigonometric functions squared and I'm trying to, simplify it, then I think about this, right? I think about the Pythagorean identities because it's likely that I can use one of them to somehow simplify the problem. Now, you can manipulate these as well. For instance, let's do this one. I could rewrite this as cotangent squared theta equals cosecant squared theta minus 1. Right? So we don't always see the Pythagorean identities the way that we have them written on the left side. You can manipulate them, they're still true. Okay, so just keep your eyes open. Anytime you see one of these functions squared, then think about using the Pythagorean identities to maybe try to simplify your problem. All right, very good. Okay, so now we're ready to start simplifying and factoring, getting our feet wet here. Okay, we got cosine beta times tangent beta. They want us to use a quotient identity to simplify and rewrite. So we know that tangent beta can be written as what? Okay, tangent is what? Okay, sine beta over cosine beta. So that gives me cosine beta in my denominator and also in my numerator. They cancel out. So this simplifies to just sine beta. Okay. All right, and they told us to use the quotient identities, but really, anytime, a technique I would say is to rewrite all of the functions in terms of sine and cosine, especially if we're hoping to cancel things out. If they've been multiplied together, then we can rewrite in terms of sine and cosine, and that's probably going to allow us to cancel things out. Okay? So for secant x, we get 1 over cosine x. Cotangent is what? Okay. Yeah, let's do cosine x over sine x. And then we got sine x, which we can think of as being over 1. And so the sine x's cancel, the cosine x's cancel. We're just left with 1. questions about that? Mm-hmm.
Why didn't you put in the square? Like, why doesn't that apply?
Which square? Where?
In the identities, it's like cosine squared beta, cosine squared beta. But why in this case are you not squaring?
I don't have a square in any of where we started. So I would only substitute an expression for a square if I started with a square.
But you're not using the identity right now, are you?
Well, I'm using the quotient identities, right, and the reciprocal identities.
But not the Pythagorean.
No, not the Pythagorean identities.
Oh, okay.
Yeah, we're not using those yet. Yes, Sophia.
What does beta represent?
An angle. Yes.
So both beta and beta, are they essentially the same thing, or are they different?
It's just like x, t. What else do we use as a variable? You know. So yeah, they're names for angles. Generally, angles tend to be, and this is not always true as we can see, but we generally name them with Greek letters. So commonly you'll see alpha, beta, and theta. Sometimes we'll talk about gamma. But it's just a different name to identify different angles. Okay? Yes?
So for secant, we did one over cosine because that is the reciprocal identity.
That's correct. We did 1 over cosine for secant because it's the reciprocal identity.
And for cotangent, that's the quotient identity.
That's right.
So would we use the reciprocal identity for sine also? Like, shouldn't that be 1 over cosine?
No, really, instead of thinking about the identity here, what I did in this problem was to write everybody in terms of sine and cosine. Right? And so, of course, sine was already in terms of sine and cosine. And we like to do that because as it happened, we were able to cancel things out.
So do you, like, when you get a problem that has multiple sine and cosine, whatever, you write it so that as many things cancel out as possible?
If I'm multiplying, that's a technique that I might try. Okay, if we're adding, then it's not as effective. But when I'm multiplying, one way that I can try to simplify is to rewrite things in terms of sine and cosine. Okay, great questions. Any other questions? Very good. All right, so we continue along. And these are different ideas. And there's, one thing about identities is, well, 2 things, I guess. There's no one way to solve it. Right? And I guess that is it. I mean, you might solve it one way, somebody else might do something else. As long as it's legal, mathematical moves, it's great. Okay? All right, so with this one, we're talking about decomposing fractions to simplify and rewrite. Okay? So what we might want to recognize is that this is cosecant theta times 1 over sine theta. So I just kind of separated the two. It's still equivalent to cosecant over sine, but I've actually written it out as multiplication, okay? And then from this point, I'm going to probably change one of these, okay? Usually we want to write it as simply as we can using as few functions as we can, and often we want to write it without having to put something in the denominator. So in this case then, I'm going to rewrite 1 over sine theta as what? Not cosine, but cosecant. Very good. Cosecant theta. And so we can just say the whole thing is equal to cosecant squared theta. Yes.
Why isn't it cosecant theta squared? Because
Okay.
theta is
Well, okay, so great question. Why isn't it cosecant theta squared? Remember, cosecant is a function, right? So it's kind of like writing f of x. Except instead of just writing f, we write cosecant, right? We actually write the name of the function. We also don't use parentheses, which starts to get a little confusing. But if you'll remember, when we first started working with these, I would write the parentheses every time. Because I wanted you to remember that we're applying this function to the thing here. So when you look at it this way, if I squared this thing, where would you put the square? On the x or on the f? And I'll give you a hint before you answer. Remember, f of x is a y value, right? It's already a y value. So in order to square it, I'd have to say f squared of x. I mean, we don't really write it that way, but it's not the x that's being squared, it's the f. And so here we got cosecant squared times cosecant squared. It's the cosecant, what we get out of it, that's being squared, not the theta. Okay? So cosecant squared theta. All right, very good. Okay, in B, we got sine x minus cosecant x over cosecant x. Any ideas of how we might approach this? Yes, you.
So, you would separate.
Ellison, sorry.
That's fine. You would separate. Look, you would write out sine x minus cosecant x times 1 over cosecant x.
We could do that. Okay, we could do that. But maybe there's something else we might do. Yes, Daniela.
Did you do? I'm gonna say something really similar to us. I think I'll take it out into sine x minus cosecant x times sine.
Okay, cosecant is sine. That's an interesting thought. All right. Yes.
Could I cancel out the cosecants?
Okay, we're getting on the right track now, I think. All right, can we just cancel the cosecants?
Yeah.
Because it's negative. Well, not negative, but there's a subtraction problem.
Okay, so what do we need to do? I can't just cancel that one, but I can distribute, right? Okay, we have to distribute it. So this is equal to sine x over cosecant x minus cosecant x over cosecant x. Okay, now I can cancel those cosecants out, but we still have one applying to sine. Yes, Ellison.
Okay. I don't want to say how, but how?
Okay, so these are still the same algebra rules that we've kind of been using. If I have a plus b over c, I can distribute that denominator to each term in my numerator. This is a over c plus b over c.
Okay, Jenkins. What about when it's a minus c over c?
Okay,
You just cancel
same
c.
principle still, nope. You still have to distribute. If this is how we handle it here, then we still have to do that. A over c minus c over c. Now when you can cancel is if it looks like this. When they're multiplied together.
Oh.
What I usually say is we cancel factor by factor, not term by term. So you gotta have it factored like this before we can cancel. All right, very good, excellent. Great questions, y'all keep them coming. Okay, so meanwhile back at the ranch, here we were. Okay, so sine x over cosecant x, I think we know how to deal with that now. We could just rewrite this as what?
Sine x minus.
I heard the sine x, and then it's going to be times 1 over cosecant x. Of course, that's going to be minus 1, but 1 over cosecant x is what? Sine x. So we got sine x times sine x. We call that sine squared x minus 1. Okay. And I might check my Pythagorean identities to see if sine squared x minus 1 is equal to anything, but I did and it's not. Okay. Questions?
I just wanted to clarify that the secant x over secant x turned into 1 and not just cancel each other out and there's just nothing there.
They canceled each other out. But, you know, so when we cancel out, I mean, there is a 1 there. It's understood to be a 1 there, so we're left with just the 1.
Yeah, like if you had, like sine x over cosine x minus 2 over 2, it would be minus 1.
Minus 1, that's right.
0.
Exactly. Okay? Very good. Yes?
Can you go over how you got to sine x minus 1 over
How did I get, right here?
before that?
Right here?
Did you just cancel out the secant x and cosecant x?
You mean this piece?
Yeah.
Yeah, the cosecants, they cancel out. And so we're just left with 1. Mhm. Okay, other questions? Very good. Excellent. Okay. So a few more examples. What about some factoring? Okay, we can factor. And, you know, you might be able to look at it and just do it because this is quadratic in type. Okay, I don't know if we talked much about that, but it fits the basic patterns of a quadratic, right? At the end, I've got a constant. In the middle, I've got a sine x term. And then my first term is a sine squared x term, right? So it's kind of like a x and an x squared term. So you can just kind of look at it that way. If you want to simplify it a little bit, then we can use u substitution. And I'm going to say that u is equal to sine x. If that's the case, then I can rewrite this as 2u squared, right? Because I got sine squared x, so that's going to be u squared, minus 3u plus 1. So just rewrote it in terms of u, which hopefully makes it look a little bit friendlier. Okay? And now we can factor that. Okay, how do I factor 2u squared minus 3u plus 1? Yes, you share.
2 squared minus 2. Wait, yeah, no. Because, like, you can do the 1, well, how I was taught when you try to, like, oh, never mind. That's wrong. Never mind.
Maybe you were thinking about grouping, which we could do that, but we don't necessarily have to. If the first term is 2u here, over here, what do we have to have? Just a what? 1u, right? 2 times 1. That's the only way we can get 2, right? And then here we're going to have a 1 and a 1, right? So the question is, what do we do in the middle? Which operations? Okay, 2 minuses. All right, if we do that, minus and minus will give us plus 1. And then we get minus 1u and minus 2u gives me minus 3. Okay, so that's how we factor it. But u is just a dummy variable. Okay, so I'm going to rewrite this in terms of sine x. And so we get 2 sine x. I'm just putting sine x back in for u, minus 1. And then sine x minus 1. Any questions about that? All right, very good. Okay, well, what about B? Do we recognize anything from factoring? Yes, Scarlett.
Are they both perfect squares?
Okay, they're both perfect squares, and we're taking the difference of them, right? So we know if we have a squared minus b squared, that factors as a minus b times A plus B. And so here I can factor this as 16, not 16, but what? 4 minus secant x times 4 plus secant x. All right, that's how we can factor that. Any questions about this? All right, just a few more, I think. All right, so still factoring, right? Some of the same techniques that we would use in factoring, polynomials, they still apply here. So when you look at C, what do you notice?
It's cosine and cosecant.
Okay, we got cosine and cosecant. All right, that's a good point. What else do you think is significant or pertinent to this problem? Where is that cosecant? Where?
Multiplied by cos.
In one of them, right? But notice that it's in both terms, right? Terms in general are separated by plus minus signs, right? And so when we have things in multiple terms, we can factor it out. So I'm going to factor out cosecant alpha, right? And that leaves me with, of course, there's a 1 understood to be there, so 1 minus cosine squared alpha. I was able to factor out cosecant, right? Because he was in both places. Okay, so we factored him out. Right, then, okay, I see that square there, cosine squared alpha. So if I need to, I can do a quick check. I say quick because I'm not even going to write the whole word out. What I should know is that cosine squared plus sine squared equals 1. And so what is 1 minus cosine squared equal to? What would that be equal to? Sine squared, right? So I can replace 1 minus cosine alpha with just sine squared alpha. And then, of course, cosecant is the reciprocal of sine. So this is 1 over sine alpha times sine squared alpha. That's going to cancel with 1 up here. And so we're left with just sine alpha. Questions about that? Yes, usually. Down here?
Yeah, before you did, like the step in between the top.
Okay, from here to here, you mean?
Yes, ma'am.
So, well, I thought this might have been one of my Pythagorean identities. So I had to kind of check, right? So this is the basic thing that I remember. Cosine squared plus sine squared equals 1, right? That's true. And so we could look back. I mean, I just tried to solve for 1 minus cosine squared. And when I subtracted cosine squared from both sides, I was left with sine. Okay, so I was able to replace all of that with just sine. Okay? Other questions? Okay, what about D? Yes.
It's cosine and
Cosecant.
cosecant and cosine. Cosecant and cosine.
Okay, all right, and cotangent, right? And so there's no way for us to factor out, so we need to get rid of one of those, right? We don't want it to be both cosecant and cotangent. How do you think we could change this?
Could you make cosecant 1 over sine and then cotangent cosine over sine?
You could, but that wouldn't necessarily help us with factoring, right? What we're trying to do is factor this. So I don't think that would be the most helpful move. Don't forget, whenever you see these squares, think about a Pythagorean identity.
It equals cotangent squared, cotangent theta plus 1.
Okay, cotangent theta plus 1. All right, so if we go back and look at our Pythagorean identities, it's not them, okay, we see that, I think I solved it right here already. What was it? I got to look at the problem again, I'm sorry. Okay, we got cosecant squared. What is cosecant squared equal to? Cosecant squared is equal to cotangent squared theta plus 1. So I can replace cosecant squared with this, okay? Cotangent squared theta plus 1. So we get cotangent squared beta plus 1, that's this piece, minus cotangent beta minus 3. Okay? And so we get cotangent squared beta minus cotangent beta minus 2. Okay? And that looks easier. Now that we've got everything in terms of cotangent squared, and a constant, that looks easier for us to deal with, right? Okay, so if we needed to, we could do our U substitution, but we could probably also do this without. Okay, but I'll do the U substitution. We got U equals cotangent beta. And of course, U squared, I don't have to write this out, but U squared is cotangent squared beta. So this is U squared minus U minus 2. And how does that factor? I'm going to have U's up there. One of these is going to be a 1, the other is going to be a 2. So what do I do with my signs?
It's gonna be a plus and minus.
Okay, plus 1 minus, I think that works, minus 2. Okay, that way in the middle, we get 1 minus 2. That gives me the negative 1 that I need. Okay, so then this is going to be just cotangent of beta plus 1 times cotangent of beta minus 2. That's how that factors. Any questions about that? All right, very good. Okay, here's another one. What do you think we can do with this? What feels natural to do? In the numerator, what might we do? Yes, we can multiply, right? And this fits our difference of squares pattern. So this is just going to be secant squared x minus 1 over sine squared x. Okay, what do you think we can do next? We got something squared up there. Yes, Scarlett.
Take square root of everything.
Can't do that because this is not an equation. We've just started with an expression. If it were an equation, then we could take the square root of both sides. But we really don't have a both sides situation here. Daniela.
Secant squared x equals 1 plus tangent squared theta. I don't know if you.
Okay, all right, she's looking at the Pythagorean identities. Okay, so let's go back and take a look at them. We got 1 plus tangent squared theta equals secant squared theta. If we subtract 1, then we get secant squared theta minus 1 is equal to tangent squared theta, right? So I can replace that numerator with just tangent squared theta. Okay, everybody see that? Oops, just tangent squared x over sine squared x. Okay, now what do you think we might do? But kind of from the beginning, one of the things we did earlier was we just kind of separated these out. Tangent squared x times 1 over sine squared x. Okay, this just multiplied still. And then now that these are being multiplied, Ellison, what do you think I might try?
Now that they're multiplying us, 1 over sine squared x equal to cosine.
Well, it would be equal to cosecant, but we don't want to go. We don't want to take the sine away. So
Great question.
let's change tangent to sine over cosine. When I'm multiplying things, that's when I might rewrite stuff as sine and cosine. Because they're multiplied, I'm going to be able to cancel, right? So earlier we were kind of talking about when would we change things to be written in terms of sine and cosine. We might do that when those things are being multiplied together.
Okay, so when you've got like tangent squared x, you write that as sine squared x over cosine squared x, right?
That's correct.
And then when you just have tangent, it's just sine over.
That's right.
Okay.
Okay? The question was, if I have tangent squared x, then when I write it as sine over cosine, both the sine and cosine are squared. But if it's just tangent x, then I don't square sine and cosine. Okay, very good. All right, but we can see that the sine squares cancel. And so I'm left with 1 over cosine squared x, which is equal to secant squared x. That's our answer. Here comes the last one. You all kind of see it, but I'll write it out again. They kind of give us some steps, right? Basically what we have here is two fractions. And anytime I'm trying to add or subtract fractions, the first thing we need is a what? Common denominator, right? So let's start by looking at cosine x over 1 minus sine x minus sine x over cosine x. Okay, well, my common denominator is going to be the product of these two. since they don't have anything in common, right? So if I want to have cosine x times 1 minus sine x as the denominator for each of these, then over here, I need to multiply top and bottom by what? Cosine x. And then over here, I'm going to multiply top and bottom by 1 minus sine x. Okay, that way now my denominators are going to be the same. Everybody see that? Okay, so then up top, bless you. I've got cosine squared x minus, I'm going to be careful here, sine x minus sine squared x all over cosine x times 1 minus sine x. Okay? That's my common denominator. Okay? If I distribute that minus sign, we get cosine squared x minus sine x plus sine squared x over cosine x times 1 minus sine x. Okay? What do you think we might do next? I didn't do that yet. Something else in the numerator.
Would you distribute the, oh, you already did that. Would you look to see if any of the Pythagorean identities?
Yes, I would check to see if I can use any of my Pythagorean identities. Okay, can I? Y'all are shaking your heads no. Very good, right? It's a really amazing tool, right? We got cosine squared x plus sine squared x. According to the Pythagorean identity, that is equal to 1. Taking that time to look at that and use it is going to save us a world of trouble, right? This is 1 minus sine x over cosine x times 1 minus sine x. And yes, I can cancel these out. All right, there's a 1 understood to be here holding his place. So we got 1 over cosine x, or that's going to be just secant x. Okay? All right, I know we talked about a lot, saw a lot, but we'll be working on this for the next few days. You do have an assignment in Delta Math. And so you can go ahead, we just got a minute, we really don't have any time, to start looking at that. And next time we'll continue to work.